Hey guys, welcome to this video on the superposition of electric fields. In this video we're going to take a look at the mathematical interpretation that we visually represented in the previous video. So if you haven't watched that one, you might want to check it out just so that this makes a little bit more sense. I'm going to jump in right away, and my goal is to show that if the two charges I have here, I'm going to name them QA and QB, if those two charges have an equal magnitude, then the electric field is going to be equal to, or the net electric field is going to be equal to 0 directly in between them. And that's what I'm going to try to show in this video. Now I have QA located at a position 2, 0 and QB located at the position 8, 0. So I can see that they are 6 units apart, and that is going to become important a little bit further on in this derivation. Now, what I'm looking at in this example is I'm just looking for the location along the x-axis where the net electric field equals 0. So I really don't need to worry about any y variables or any z variables or anything like that. So that should make this a lot easier. Now, essentially what we're going to do here is I'm going to draw electric field vectors, how they are contributed by each of the individual charges. So in other words, QA has an electric field vector pointing in this direction, and QB has an electric field vector pointing in that direction. Now if I look at the two vectors, I can label them as E sub A because it's the electric field made by QA, and this side is EB because it's the electric field made by QB. Now because I've said QA and QB are the same, we already know that EA and EB would have to be the same if we're comparing the same location. But I want to show the proof of this so that if QA, excuse me, if QA and QB are not the same, that you could still solve the problem. Now, when we are looking at electric field vectors, we remember that vectors have a orientation or a direction associated with them. So I'm going to use the traditional coordinate system, and what I'm going to say then is that EA is a positive vector and EB is a negative vector. Because of this, when I add the two vectors together, it actually ends up with me subtracting them from one another. So what I'm going to say here is that the net electric field in the x dimension is equal to EA, just in the x is what I'm looking at, minus EB in the x, and that's all going to add up to 0. Now I know that the electric field equation that we came up with before is equal to K times Q over R squared. And if you remember, R is the vector that could be radially out from our charge, but I can also make it x comma y comma z if I wanted to, and I can get rid of y and z because I can see that there really isn't any issue. We're only looking for the position along the x-axis. So essentially I could make R x in this case, and that would be alright. So what I'm going to do here is I'm going to substitute in this expression for EA and for EB appropriately. So I'm going to say K times QA over, now I'm going to put x sub A squared, and this side I'm going to put minus K times QB over x sub B squared, and that's going to equal 0. Now the issue I have here is that the way that I have it set up, QA and QB are variables, XA and XB are variables, and I would have too many unknowns if I was trying to do something like this. So I'm going to try to write XB in terms of XA, so that would make us find one location rather than the distance from the QB particle and the QA particle. So a way that I can do that is write K times QA over XA squared minus K times QB over, I'm going to put the expression in here, 6 minus XA, and if you remember that this is squared, the square will go on the outside of the parentheses. Now when I look at that, it makes sense because if these are 6 units apart, the position where it's going to be equal to 0 away from XA is just XA. but the position away from QB is going to be 6 minus what the value of XA is, and that's inadvertently going to give me XB. Alright, so at this point, what I'm going to do is set these two expressions equal to each other because they both sum to 0. So if I add this term over to this side, I end up with KQA over XA squared equals K times QB over 6 minus XA squared. Now at this point I know that K is a constant that's the same. I can factor it out. I've stated that QA and QB are the same, so I can factor those out. And now I'm left with these two expressions. And I'm going to take the reciprocal here, and so I'll be left with x sub a squared equals 6 minus x sub a quantity squared. Alright, let's make a little bit more room here. At this point, what I can do is expand this on the side here, and that's going to give me, let's see, 36 minus 12 XA minus XA squared, just like that. Okay, at this point, what I'm going to do is I'm going to add up some of, or actually this will be a plus XA squared, my bad. Alright, what I'm going to do here is I'm going to combine some like terms. So I'm going to do minus XA squared on both sides. That's going to leave me with 0 is equal to 36 minus 12XA. And then if I add 12XA to both sides, I have 36 equals 12XA. Divide by 12 on both sides. And I'm left with XA is equal to 3 units. In this case, I didn't state what they were. So basically what we're saying is that at 3 units away from XA, so let's see, 1, 2, 3, the electric field is technically supposed to be 0. Now let's see what the distance from XB is, and it should be the same because they have exactly the same magnitude of charge. So my expression for XB was 6 minus XA. So if I put 6 minus 3 in there, I do get 3 as my distance from XB, or from QB. So I'm going to do from 0 here, 1, 2, 3. Yep, that is the same location, and it does work that they are 0. Now let's say we had a scenario where the value of A was 2Q and the value of B was just Q. And we wanted to show that, and there should not be an equal sign here, we wanted to figure out where the electric field was going to be equal to 0. Well, I'm not going to go ahead and solve the entire thing, but I will set it up for you over here. And the step that would change would come in right over here. The two vectors are still opposing each other, and so they'll be subtracted and be equal to 0. But what we're going to have to do at this point is we're going to have to put 2Q for this first one, so 2Q times K, or 2KQ, over XA squared minus QK over, and we'll have the same expression here, 6 minus XA squared, and that's going to equal 0. So you can see here that this factor of 2 now is going to adjust where the location is equal to 0. And so if you think about it, it will be closer to the one that is a weaker charge value. So the electric field location that is 0 would move over this way a little bit and be positioned somewhere over here. And we could prove that and solve for XA. So as you can see, this is really just vector addition, which we've done with so many different things in physics up to this point. The key things about electrostatics here are remembering that if you have a positive and a negative charge, things would be different because the electric field lines would point in different directions. And so to end this video, I'm just going to show you how we would set up the problem if we had a positive and a negative charge. So let's say that I have a positive charge here, still at the same location, and over here I'm going to place a negative charge. I'm going to say that QA and QB are still the same magnitude and they're still equal to one another. But at this point, the only thing that's going to be different is that the electric field in between them, E sub A, points to the right, and the electric field between them, E sub B, also points to the right, because it has to point towards the negative charge and away from the positive charge. And now you can see that we'd really be doing EA plus EB, and this is not possible to equal to 0. And so what we could do is we could rather say, what is the value of the electric field in between them? We could use that to help us calculate the value. And we could have to pick a specific location right in between them. So we could say at the position right in between where x is equal to 5, I guess that would be what is going to be the net electric field strength. So you can see what a powerful process this is, and the main thing about electrostatics is just to make sure that you draw in the vector directions based on what the charges are before you start trying to add anything algebraically. Well, I'm wishing you luck on doing some of the problems with this. They can get a little tedious algebraically, but don't worry, stick with it and you'll get better at it.